In this problem, I'm going to be doing another optimization problem involving the optimization of resources. The Skagway Coffee Company has placed an order for cylindrical cans with a volume of 354 cubic centimeters. What should be the dimensions of the cans to use the least amount of metal in their production? So the first thing that you want to do with an optimization problem is determine what your objective function is going to be. So the objective function is always that which we want to maximize or minimize. So what is it exactly that we want to maximize or minimize? Well, it tells us what should be the dimensions of the can for the least amount of metal. So if you think about it, that is going to be what we call surface area. So let's just draw a picture of a can. So a typical can has a cylindrical top and it has a cylindrical bottom, a typical soup can, let's say. And so we want to minimize the amount of metal that will create that can. So that is called the surface area. So surface area is what we want to minimize. Well, how do we find the surface area of a can? Well, the surface area of the can consists of three parts: the top plus the area of the bottom plus the area of the sides. Well, the area of the top, the surface area of the top, if we look at the top of the can, it's a circle. And so we know a formula for the area of a circle. It is pi r squared. Well, the bottom down here is also a circle. And so that is also pi r squared. Now, what about the area of the sides of the can? Well, take out a can opener and cut off the top, cut off the bottom. And when you do that, all you're going to have left is the sides of the can. And if you cut open the can vertically, just make a gash right down here and open it up, what you're going to see that you have is just a great big rectangular piece of metal. And the height of this can would be the height of this. This would be the height. And the length of this sheet of metal would be the circumference of the can. The circumference of the can, or the distance around the can. That is the circumference. Well, the circumference is equal to the diameter times pi, and diameter is 2 times the radius, so 2 pi r. So this distance here is 2 pi r, and this is h. So the area of the can, since it's of the sides of the can, since it's a rectangle, is length times width. So it would be 2 pi r h. Okay, area is length times width, which is 2 pi r times h. All right, now, since the top of the can and the bottom of the can are both circles, we can combine those and say that the surface area is 2 pi r squared plus the area of the sides, 2 pi r h. So this right here is our objective function. All of that work just to find the objective function. This is what we want to optimize. In this case, we want the minimum amount of metal to create the can. Well, notice that in the objective function, we have two variables. We have r and we have h. And so the rule is, if your objective function has two independent variables, then you need to come up with a constraint. So we now need to find a constraint function. So we have to go back to the problem and say, well, where is our constraint in this? The only other information that we're given is that the volume is 354 cubic centimeters. So we're going to have to work with that. So the volume of a can would be pi r squared h. This is the general formula for the volume of a can. And we know that the volume has to be 354, so I can substitute that in for V. And this is my constraint. That is my constraint function. Remember what the constraint function does. It relates the two variables in the objective function. So we have r, and r was in the objective function, and we have h. But what we now have to do is we have to solve this for one of those variables. So I'm going to solve it for h. So if we do this, we're simply going to get h is equal to 354 divided by pi r squared. And that is my constraint function solved for r, or solved for h. Solved for h. So in the 5-step process that I outlined in another video, the first step is to find the objective function. We've done that. The second step is to find the constraint function. If you need one, we've done that. The third step then is to substitute the constraint function into the objective function. So what we're going to do is we're going to remove h and we're going to put in all of this stuff in its place. And so what that's going to look like would be something like this. We have the surface area. Surface area was 2 pi r squared plus 2 pi r h. And I'm now going to substitute in for h, 2 pi r. And what was h? 354 over pi r squared. Now let's simplify that. Well, this r cancels with one of those r's, and pi cancels with pi, and 2 times 354 is going to be what, 708. So what we have now is surface area is 2 pi r squared plus, and we're going to have an r in the denominator, 708 over r, which of course we're going to want to change to 2 pi r squared plus 708 r to the negative 1 so that we can take the derivative of that. All right, so this is our simplified objective function ready to be optimized. So we have now completed step 3 of the 5-step process. The next step is to optimize. We now want to optimize. And so what does optimize mean? Optimize means we take the derivative. So we want to find the derivative of surface area, SA prime. And so the derivative of this would be 4 pi r, 4 pi r, and the derivative of this would be negative 708 r to the negative 2. So that is the derivative. And then what we want to do is we want to set the derivative equal to 0. Set it equal to 0 and solve for r. So the first thing I can do is I can take out a common factor of 4. I can take out the lowest power of r. So once again, this is r to the first, r to the negative 2. we're going to take out the lowest power of r, which is the -2. And then what I'm left with is pi and r to some power. Well, this power added to this has to be equal to this. So this has to be 3. 3 plus a -2 is 1. And 708 divided by 4 is 177. And we took out the r to the -2. Set both factors equal to 0. So we have 4r to the -2 equals 0, or 4 over r squared equals 0. And once again, that's going to give us 4 equals 0 when we cross multiply, which gives us nothing. That is a fallacy. That is a false statement, not true. So we have pi r cubed minus 177 equals 0, or r cubed equals 177 divided by pi, or r is equal to the cubed root of 177 over pi, which is approximately 3.83. And that would be our r value, rounded to 2 decimal places. Now, in the homework problems, they may be rounded to 1 place, they may be rounded to 2 places. In some cases, it'll say to round to the nearest integer. All right. So I'm just going to leave this to 2 decimal places. So the radius of the can needs to be 3.83 centimeters in order to minimize the surface area. And we're not done, because we need to find h. Well, how do we find h? Well, we have to go back to our formula, volume, our constraint, volume equals pi r squared h. And so remember, this was 354 equals pi r squared h, which gave us h was equal to h is equal to 354 over pi r squared. So that means we have 354 over pi times 3.83 squared, which is going to give us approximately 7.68. And so there is our height. So the dimensions of the can that would give us the minimum amount of material to create this can would have to have a radius of 3.83 centimeters and a height of 7.68 centimeters. Now, one last thing that we want to do to verify that this is indeed going to minimize rather than maximize is we want to find the second derivative. So our first derivative was up here. This was our first derivative. Let's take the second derivative of that. So the second derivative of that, we'll do that down here. This is the second derivative test. In some homework problems, you're going to be asked to do the second derivative test. And so the second derivative test, you start with your first derivative, 4 pi r minus the 708 r to the -2. And you find the second derivative, which in this case is going to be 4 pi. And so we're going to have plus 1416 r to the -3, which would be 4 pi plus 1416 over r cubed. So remember, what we do then is we evaluate this at r. So if we evaluate this at r, if we take the second derivative evaluated at 3.83, we're going to have 4 pi plus 1416 over 3.83 cubed. Well, this whole thing is going to be positive. Remember, I don't care what the number is. I just want to know for the second derivative test if it's positive or negative. If this is positive, that means the graph is concave up at that point, which means we have a minimum which is what we wanted. We wanted to minimize. So this is guaranteeing that what we found was indeed a minimum. All right, so that is everything that you need to know about this particular problem.